let's continue our discussion of drawing Lewis dot structures, but this time we're going to move from diatomic elements to compounds. Either we can call them molecular compounds or covalent compounds. In either case, the bonding is covalent, but what's new and different here is that instead of looking at just one kind of atom, as was the case with hydrogen, oxygen, and nitrogen, compounds have two or more different atoms present in their structure. How would we draw a Lewis dot structure for a molecular or a covalent compound? Your textbook lists steps for drawing Lewis dot structures. You need to know these. The way it works is that you just have to use them. You know them by using them for the examples that you will be given. In Chem 2A, the steps are found on page 196, steps 1 through 4. In Chem 22, steps 1 through 4 are found on page 330 and page 331. Now you can open up your textbook, you can read those steps, and you should certainly spend time. They give you more information and detail about each step than I am able to put up here on the board right now, but I've given a quick synopsis of these steps so that we can apply them to the two examples that we have up here on the board. So step 1, you determine the bonding arrangement of atoms. What's bonded to what? We can refer to this as a skeletal structure. And what's a very helpful guideline when you're first beginning to draw Lewis dot structures is that if you look at the formula of the compound, so here we have phosphorus trichloride, we see 1 phosphorus and 3 chlorine atoms present in the formula. What's helpful to remember at the beginning is that if there is only one of one kind of atom, then it is usually or often the central atom. If there are many of other types of atoms present, or many of another type of atom, let me speak more clearly, there's 3 chlorines, then the 3 chlorines are usually terminal atoms. So we've done step 1, we've come up with a bonding sketch for phosphorus trichloride. Now we're moving to step 2. We want to count the total number of valence electrons that we have present in the molecule. So you're going to need that periodic table right in front of you to quickly identify valence electrons from the group number for the A families. So chlorine in family 7A, that means that it has 7 valence electrons. The formula says that we have 3 chlorine atoms, so 3 times 7 is 21. Moving to phosphorus, which is in family 5A, phosphorus therefore has 5 valence electrons, and totaling all the valence electrons that our picture should show, 21 and 5 is 26 valence electrons. So we've got that count, and from me to you, if you're being quizzed or tested on the material, it's a good idea to add it up again and make sure that you haven't made an addition error. It's easy to do, and then it will throw your whole structure off if you're not dealing with the correct number of total valence electrons in the drawing. So just checking again, phosphorus 5 valence electrons, each chlorine 7, 7 times 3 is 21, and 21 plus 5 is 26 valence electrons that we should be showing in our picture. And let me just move that so it's all in a line. Okay, so we've completed step 1. We have a skeletal structure, a bonding sketch. We've completed step 2. We've counted the total number of electrons. I should point out here, and your book discusses this in greater detail, that if the species that you're looking at is an ion, a polyatomic ion, then you will need to account for the charge on the ion. If it's an anion, that means it has 1 or more extra electrons. that you need to add to the total count. If it's a cation, then it's missing one or more electrons as indicated by the charge, and you'll need to account for that in the total count. So now we're going to move to step 3. We're going to begin the bonding using single covalent bonds only to begin with. So I'm here and I am connecting the phosphorus to each of the chlorine atoms using a single covalent bond. Always begin using single covalent bonds. And then we're going to complete the octet of the surrounding atoms first. Not the central atom, but the surrounding atoms. So chlorine is surrounding the phosphorus, and we are going to complete the octet of the chlorine atoms. So I'm giving each chlorine an additional 6 electrons to complete the octet for each chlorine atom. And quickly looking here, remember that the dash represents 2 electrons being shared. So 2, 4, 6, 8. This chlorine has 8 electrons, and we see the same thing applies for the other chlorine atoms as well. Right? So stopping and looking at our picture, right, we see that we have a total of 8 plus 8 plus 8 electrons showing right now in the drawing. That adds up to 24 electrons. But our picture must account for 26 electrons. So we have 2 extra electrons to place. And we come and we see phosphorus doesn't have an octet. So 2, 4, 6 extra electrons would therefore be placed on the phosphorus atom, those 2 extra electrons. And now I can see that phosphorus's octet is complete as well. 2, 4, 6 electrons plus a lone electron pair makes 8 electrons. And every atom has an octet, and the total number of valence electrons that my picture is showing is 26 electrons, which is the correct count. So when you are checking your structure, when you're finished, does it look good? These are the things that you have to ask yourself. Does it have the correct number of valence electrons in the picture, the correct total number? It must have that correct number in order to be a valid structure. And does every atom have an octet? Does every atom have an octet? With the exception of hydrogen, of course, that follows the duet rule. If both of these criteria are met, you have the correct total number of valence electrons and every atom has an octet, then you have good confidence that this would be a valid Lewis dot structure for the molecule. Let's go and take a look at example number 2, which is carbon dioxide. Looking at this formula, we see 1 carbon atom, 2 oxygen atoms. So drawing our bonding sketch, we're going to start out assuming that oxygen is the central atom. That carbon is the central atom, and that each of the oxygen atoms are bonded to the central carbon. There's only 1 carbon atom, we'll place it as central, 2 oxygen atoms, and we will use symmetry principles and balance. In other words, it makes sense to have this symmetrical structure rather than putting an oxygen atom over here, which gives us an unbalanced drawing. So using symmetry principles and the idea that multiple of one kind of atom are usually terminal, we'll start out with this bonding sketch. So step 2, now we have to count the total number of valence electrons that are present in the molecule. And we see that it is not an ion. There's no charge here. It's a neutral molecule, so we don't have to make any adjustments because of a charge on an ion. This is not an ion. So periodic table shows that oxygen is in family 6A, 6 valence electrons. There are 2 oxygen atoms. 6 times 2 is 12. Carbon in family 4A has 4 valence electrons. So adding those 4 electrons, we come up with a total count of 16 valence electrons. And again, if this is a quiz or an exam, it's a good idea to double check that count. So we've completed step 1, we've completed step 2, and now we're going to start bonding the atoms together using single covalent bonds only. So single covalent bond, let's make it pop a little more in blue. Single covalent bond, single covalent bond, and then we must complete the octet of the surrounding atoms first. So I'm going to quickly put 6 electrons around each of the oxygen atoms to complete their octet. So stopping and looking at this picture, I see that each of the oxygens now has an octet, but carbon does not have an octet. So my first instinct may be, oh, well, carbon does not have an octet. I need to give carbon 4 more electrons to give it an octet, but wait a minute. If I do that and count the total number of electrons that I'm showing in the picture, valence electrons, I have a problem. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have too many valence electrons in this drawing for the total of number of valence electrons that I have to work with. So this cannot be the right structure. If you don't have the correct total number of valence electrons showing, your drawing cannot be the correct drawing. So I'm going to have to back up and remove those extra electrons that I placed incorrectly on the carbon atom. I don't have those electrons to work with. So that's where step 4 comes into play. If the central atom lacks an octet, form multiple bonds. And that's what we have in this situation. Now, how do we form multiple bonds? Well, we look at the surrounding atoms, the oxygen atoms, and see that they have unshared electron pairs that could be brought down and become shared electron pairs. So I could form an additional bond here, but that would only give carbon a total of 6 electrons. I'm going to need to form 1 more bond to give carbon a total of 8 valence electrons, and symmetry suggests that each oxygen donates 1 unshared electron pair. So this gives us a final Lewis dot structure of this for carbon dioxide. Looking at this final structure, Lewis structure that we've drawn, let's ask ourselves the 2 important questions. Does it show the correct number of valence electrons, total valence electrons? 2, 4, 6, 8, 10, 12, 14, 16. Yes, it shows the correct total number of valence electrons. And does every atom have an octet? So doing a quick check here, I see this oxygen atom within the circle, 2, 4, 6, 8 electrons. Looking at the carbon atom and counting electrons around the carbon, I see a total of 2, 4, 6, 8 valence electrons. And our last atom, our oxygen atom, 2, 4, 6, 8 electrons. So yes, we have met the second criteria. Every atom has an octet, and that gives us confidence that this is a valid Lewis dot structure for carbon dioxide.